All right. Yeah, all right, let's see. So, just a reminder that we do have a test coming up in class. It will be in class, okay, just like the last one. So as usual, I will do some runs of the autograder. It will not be running continuously. I will just run it a couple of times, or well, for a couple of hours or whatever, on Monday and Tuesday nights, just to get things, well, just to give you some idea of what's going on. So those of you who have submitted, great. Those of you who hadn't, well, okay. So it goes. Those of you who are interested in determining whether your program, whether your testing is complete, might be interested in looking up the documentation for the, the new program GCOV, G-C-O-V, which is a coverage tool. It basically looks at your program. You run your program, and it tells you what things you have run, what things you have executed, or what pieces of code you have executed, and what pieces of code you haven't executed, which gives you some idea of whether you've tested, how much of your program you've actually tested. I think I will be trying. I'm going to try to incorporate that into our own testing. The idea being that to assess your test programs, we just run this thing and on our machine, on our solution, and see how much of our solution your tests exercise. And so that's just so you know how these things can be done, I guess. Now, on the subject of testing, by the way, I guess I was not terribly precise last time about test sharing. I really prefer that each team develop its own tests, simply because that's the way you learn how to develop tests. Certainly do not rely on the autograder tests. We will, as we did for Project 1, we will filter those out when looking to see how good your tests are. Okay, questions? No questions. Okay, well, that's good. Or maybe that's good. Maybe you're just tired. All right, let's hope not. All right, let me get back to where we were. I see, I keep hitting these two buttons simultaneously, and that's not good. All right, so last time, we were in the process of looking at how you deal with this case, the case of functions properly nested inside other functions, where all of the calls, where you're able to get at the variables of your enclosing functions, and all of the calls are to names that have been deffed, to basically constant function, known constant function destinations. So the compiler basically knows what code is going to get executed when you do each one of your calls. All right, so that's the situation. But of course, and by the way, this actually, well, all right, let's hold that thought. Now, if we look at a language like C, for example, even a language like C, you also, and Fortran, I might add, this goes back a long way, you had the ability to pass a function as a parameter. Now, where this differs from CS61A is that functions in C and in Fortran have the property that they weren't nested inside anything else. The only variables that you can access in such functions are the local variables of the function or procedure, and the global variables which are at static locations. The local variables are at static locations relative to the stack pointer, or if there's no recursion, static locations period, and the global variables are at static locations in general. So that means that there's no issue involved in accessing non-local variables. Right? Now, suppose, however, that we allow function nesting and we allow functions as values as well. Now all of a sudden things become complicated because if you think about back to the representation that we had before, you're passing an extra parameter to each function, namely the static link to this function. And you need more than, and there can be different static links. If you call the function from, if you get the value of the function at various points, at those various points it will have different static links. And so if you call one of those instances, one of those evaluations of the function, you presumably should somehow get the right static link, and somehow, and we have to make provisions for that to happen. So the first assumption, to make things life simple for us, we can assume that otherwise the situation is the same as it is now. When you call a function, when you call a function, all of the enclosing functions, all the functions that are enclosing it, are still running. Or I should say all the function instances are still executing. So in other words, the access to these functions is itself is properly nested as far as the lifetime as the function is concerned. Well, in that case, what do? Well, we go for the environment diagrams, and here you are. Instead of the double bubble, I have a double square, but it's really the same idea as in 61A. So when you evaluate G, which you would do right here, so here's a call to H1 where we pass in a function F2 as the parameter, and here is a function H1 where we call that parameter. And presumably, although here I don't do it, but presumably elsewhere, G could or H1 could be passed other functions. So you can't, if you are going to make one body for H1, it had better be prepared to receive any possible function. You could pass it. Not only G, which is not only F2, which is nested inside F1, which is nested inside F0, but also things that are nested just inside F1, or things that are nested just inside F0, or things that are nested that are global, or possibly things, who knows where that G came from. You can arrange through a sequence of calls that G comes from some entirely different nest of functions that's not nested inside either F0 or F1. So how do we handle all of those cases? Well, you do it the way that you do in 61A. The value of this parameter, the value of F2 that I pass, has to be something like this. It has to be an affair that contains not just the code of F2, not just a pointer to the code of F2, but also a pointer to the somehow a way of referencing the frame in which I evaluated F2. So that way, when you actually call G, you will give F2 access. You will know to give F2 access to X, Y, to X and Y, which are defined outside it. So this is really exactly what you've already seen in 61A. We define that if we were to actually call F2 directly, to say F2 of something, print H1 of F2 of something, then we would pass to it, from last lecture, we would pass to it the address of this frame, F1's frame, so that it's able to get at the variables in F1 and thus the variables in F2 and so in F0 and so forth. So we'd pass that address. So when we compute the value f2, in other words, we don't call it, we compute the value. What is f2? Just what is that value? We will compute we will save the appropriate static link that we would have passed if we had called it. And that's what goes in the left-hand side box here. So static link and code. And with the static link representation for functions, calling this thing is easy. It's a very easy step from what we did before. Namely, you simply say, all right, I will call this function just as I would in ordinary code, except, well, not quite. I would call the function. I will call the function by picking up this address here. I don't know what that address is, but it's there in the value, so we'll pick it up. And I will figure out the static link parameter by looking at this box right here. And so the thing that gets passed as my parameter is some sort of access to this double box. And that's it. Very simple. A very nice implementation, works perfectly as long as these functions remain properly nested in lifetime. But the global display, on the other hand, that is this using an array instead of a linked list for accessing frames, that suffers. All right, so this is a global variable here. Now, if I'm going to use that implementation, in other words, if I'm going to arrange that this global array right here always has the address or has the addresses of all of the functions I'm nested inside at each point in the program, if I'm going to arrange for that, and I'm going to have function values that I can pass that can be evaluated from nested functions, what am I going to have to do what am I going to have to do to make that work? So based on what this representation contains, I'm asking you to figure out what has to happen when I call a function, when I return from a function, and when I call a function and when I get the value, pass the value of a function, what's got to happen? Yes? Yes, basically that's what you have to do. You have to when you evaluate F2 back here, right here, I'm sorry, let's go to one. Yes, when I evaluate F2 here to pass it, I'm going to have to keep around a copy of the current value of the display because, or at least of those elements of the display that F2 might use. So that means that the amount of data that I have to store is variable, which is always a pain. And it also means that it's rather, with the global display thing, it's a bit expensive to, it turns out to be just a bit expensive to access functions. It's not terribly pleasant to call these things. So, I'm sorry, to call function values. On the other hand, I think you'll find that if you were to look at programs dynamically, the percentage of time that you actually do that, the percentage of the program that you actually spend doing that kind of thing is very limited. So it perhaps is not such a bad trade-off if you like the fact that the global display is generally faster for other purposes. Well, okay, so there you go. But that, by the way, is an interesting example. Again, an interesting example of the interaction of language design and implementation. The global display was a really nice solution as long as we didn't have this feature. As soon as we add this feature, then global display becomes more problematic because you have to adjust somehow for it. You have to save more data. Okay, well, that's good. Now let's go all the way back to 61A. Right? So it's always interesting that when you advance in our program sequence, you go to more primitive languages as you go along. It's kind of a feature. So here we are, and we have this typical function. We have a function incr, and I'm going to, and in it I'll just save a local variable. That's because the way I've been doing it, I'm sort of boxed myself into a corner here. The way I've been doing it, the status of parameters is a little bit unclear, so I thought I would eliminate that ambiguity by just introducing a random local variable that saves the value of the parameter, and then we call this function f, and f will access that local variable of incr. But at that point, incr returns. So at the point that you actually get around to calling f, you return the value of f. At the point that we actually get around to calling it, increment will have completed execution. Increment will have completed execution, and all of a sudden, that is if we do this naively, and if we use that technique that we did before, we'll be in trouble. We will have returned a value that's pointing to garbage storage. So there's something wrong with this. This doesn't work. So as a solution, extending what we have at the moment to general closures, as these are called. F is called, the value f that's returned is called a closure. Doing that extension is not terribly easy because it is not an immediate extension. So this particular addition to the language to the language semantics is really kind of difficult. Which is why you find in other languages that allow this, for example, Algol 68 allowed this sort of thing, but it had these careful rules that made it impossible to produce this kind of situation. So you could return a function that accessed non-local parameters, but you could never call it after you left the function that defined non-local variables. But you could never. But it was arranged that they had to be non-local variables that were far enough outside that they were still around when you actually got around to calling that function. In the case of C, again, this is not a problem because there aren't any variables that disappear, that can disappear when you return from a function, or any variables that you can access that would disappear when you return from the function. So that means that we have to do some work. And specifically, there's really not much for it. An arbitrary amount of information has got to be stored every time that you create such a function value. So that means that when you call this, what we'll have to do is we'll have to save up all of the local variables for the incr procedure and put them onto the heap and access them from there. Now this can cause a little bit of consternation because, of course, you generally would like to put things on the stack, which means that you can do that as long as you don't do this fancy trick of returning this function f. So you have this problem of, okay, fine, you've just called me. Am I going to allocate my local storage on the heap, or am I going to allocate it on the stack? Or am I going to allocate it on the stack, and then when I discover that I need to keep it around later, I should make one of these things. Right. So that's a little design decision you have to make. Another thing you could simply say, as some do actually, as some implementations do, well, The heck with it. We'll use, instead of using an array representation for our stack, we'll use a linked list. We will allocate all the frames in the heap, and we'll link them together, and everything's solved because all I have to do then is unlink when I create one of these closures, I just unlink the appropriate frame, and I use that, and I don't ever release these frames except by garbage collection or something like that. So that's been done. Yep, that's been done. The important thing is to understand that there is this consequence for that language design, that simple language design decision. It's just one simple thing. All I did was I said, from now on, I can do this. I can have a return of f. Before, I could return functions as long as they were outer level functions, but now I'll allow you to return any function. Just a small, one little line in the reference manual causes untold pain to the implementer. So that's how you do it. All right. Okay. All right, so now you might think, oh gosh, well that's kind of fraught, but I'll bet that's as bad as it gets, right? Well, let's see. That's fine. The frame can disappear harmlessly. That's nice. Now, we have one more thing to do, and that's the continuation. Now, continuations are a fascinating language design or a language feature. As far as I know, they got introduced as a theoretical device to describe the semantics of programming languages back in the 1970s. And then somebody had the bright idea of saying, gee, this would be an interesting language feature. Let's put it into our language. And so it went, and so they started doing languages that way. I think that's what happened. I don't know. I should look into that more closely. All right, so here's how the thing works, or here's what the idea is. A continuation is you can sort of think of it as a snapshot of the stack, quote unquote, that is, of the current state of which functions have called which functions and what their next and where they are in the execution of the code. So it's all of that. But with the local variables and so forth being separately modifiable. So this is a rather convoluted example in which I compute this function, call with continuation f. And what that means is that it is a function. C will then, after this call, C will be a function that when called causes the program to drop whatever it's currently doing and jump to this point right here in the program with the same nest of calls, whoever it was that called, whoever it was that called G, that had called G right here at the point where I am about to execute this, when I finally get around to calling C, that same situation will be restored, and I will have the same sequence of calls on my calls, same sequence of things to return to. And further execution of, for example, right here, when I call C, further execution past this point gets abandoned, and we just return the program to the state we were in, or to the control state we were in right here. I say control state because the variables may have been updated in the meantime. That's sort of the confusing part. But the control state is here. Now, so this is really weird. This is sort of what happens. You can work out the implications here. This is one of these examples that I put up on a lecture and then I ask you to meditate on later because, and when you do, you will sort of understand what happens. So here is this function. I do this, I start off with G2, so G comes through here and it does this recursive call, gn-1 and so forth, and it finally gets around to the situation where it calls with n equals 0, at which point it gives me this continuation, and it first prints this, and then it gives me this continuation. It prints B, and then it returns, prints C, and then after I've unwound myself from this loop, I go in here and I call C again, and it starts me right back up where I left off up here, but with new values of x and n, with the values of x and n that have been incremented at that point. Now, what might this thing be useful for? It was originally used in describing things like the semantics of the goto statement, for which it's actually kind of useful. You can use it. I mean, this is exactly the sort of behavior you want in the case of exceptions, for example, which we will be talking about next, in which you'd like to say, execute this piece of code, but if anything goes wrong, then come and do this. Come back and forget all of the execution. If anything goes wrong, then forget all of the execution, come back here and do this other thing. So that's exceptions. You can also use it for things like threads and coroutines, not parallel threads, but coroutines, basically. That is, you can think of as threads that execute sequentially, in which what you want to be able to do is to say, abandon execution here and take it up over there. Now I'm executing this piece of code, stop for a moment, go back and go to whatever you were doing in that other piece of code, do that, and then at some point it decides to come back to where you were. That's the coroutine thing, except it's not like function return where you always go back to the same place. You can actually go sort of round robin, where function F1 executes for a while, then it calls function F2, which executes for a while. Function F3 executes for a while, and at each point they save each one of these things, F1, F2, and F3, saves the next point of execution in some continuation variable. So you can use it for that purpose. But how do you implement this thing? This is really general, and there's actually nothing much for it. You basically have to allocate things on the heap, and it's the nature of the continuation that this time, instead of just a stack frame you're putting on the heap, you're putting some sort of representation or some distillation of the representation of the entire stack on the heap. So each one of these things is in general a little stack. And there are clever ways of doing this, so it isn't quite as bad as it sounds. But nevertheless, this is definitely a feature that has rather larger costs than any of the other features we've seen. And yet, you will find it in some of the more advanced programming languages. So it's really neat. If we had to do things this generally to implement exceptions, however, we wouldn't implement exceptions. But fortunately, it turns out there are better things that we can do. There are better things that we can do for them. Okay, so here basically is just a summary of everything we've done in the last couple of lectures on functions. So showing the various feature levels. So at the outset, in the beginning, there was Fortran. No recursion, no nesting, and it was easy. You could put everything. You could do everything statically, or you could use inline expansion. Great. All was paradise. As soon as we throw in recursion, we have to have a stack. As soon as we throw in, if we want to have variable size data on that stack, then we need to keep track of both the top of the stack and the base, the frame pointers. If we want to be able to pass functions as values, then assuming that we keep everything nicely nested, we have to add some sort of static link or other display to allow a function to get it at the variables of the things in which it's nested. Then if you want, in addition to not only have parameters that are functions, you'd like to be able to return functions as values, well, then you're going to have to store the static link. And if you want them to return them as values, and in addition, you want them to survive, those values to survive the functions in which they were created, then you'll need to start putting stack frames on the heap, or the equivalent of stack frames on the heap. And finally, if you want continuations, you have to put the stack on the heap as well. So things become interesting as the power of the features increases. All right, so that's basically my summary of function implementation. Issues? Yes. Yeah. You mean you're saying C++ has continuations? Not really. I mean, it has threads, which essentially do this. I mean, they have. That is to say, if you not bare C, but C with POSIX threads has this. But it has no provision for within the language itself that would allow you to do this kind of that provides this kind of thing. The thread library does some technically illegal stuff behind them that's sort of blessed by the implementers to make this happen, but it's not part of the language, no. In either C or C++, I think. You may be thinking of something else, I'm not sure. I mean, you're not thinking of pointer to member functions, perhaps, or something like that. Yes. Uh-huh. There are exceptions in C++, yes. There's an exception mechanism. But that's a very limited form of continuation, as we'll see. So, yeah, you can do that, yes.
I think he's talking about the function setjump.h.
Yes, well, that's right. So we'll be talking about that next. That's a very specialized form of continuation, a very specialized and imperfect form of continuation, yes. All right, let's take a break and maybe open some doors or something, since I can see that you're all being lulled into a state of somnolence by the wonderful heat that we're having today. So let's take a break.
I have a quick question about subtyping rules.
About which?
Subtyping rules for function types. Could you quickly explain the intuition behind this rule that says that for each of the argument parameters, the function type is, sorry.
The type of the parameter has to be a supertype of the...
Yeah. Why is it that way?
That's called contravariance, and it's because if I have a variable or a function variable, and I assign to this some function f, all right? Now, I am going to be calling A, and I want the compilers, I want the type rules to be such that this call will not cause a problem when I call A of something, A of X. I don't want that to be a problem. So what should I be checking for? I should be I have to make sure that this parameter X is going to be acceptable as an argument to F, right? Well, it won't necessarily be acceptable if F's parameter could be a subtype of A, because only if it's a supertype of A. But when it comes to using the value that I get from A, assigning that to something, well, then the usual rules apply. I want the value returned by f to be some subtype of b because I expect this to be of type b.
Yeah.
I expect it to accept an argument of type x, and I expect it to return a value of type b.
Okay. Okay, that makes sense. Thank you.
So it's yeah.
Yeah, I just looked it up. I'm talking about the jump statement.
Set jump.
Just like this jump to the label. Like let's say you have label called fruit. So it's like go to accept instead.
Okay. Well, I'll have to look that up. That's one I'm not familiar with. It's not.
You said it transfers the immediate flow of control to the label you're going to. It might just be visual sequence.
Probably.
Yeah.
I don't. I mean, if so, it's. I mean, you have to have quite a bit of mechanism to be able to do that. So. I mean, it might be that it's just. It might be just an extension of the exception mechanism. So I'll look it up and see what it is. All right, let's get started again. So first of all, a quick word on the project. Now I know that there's a great deal to do in this project, so oh yes, by the way, I have all but 4 of the project ones graded, and they should have been returned by now. So that is to say that email comments. So those of you except at the end of the alphabet, you should whose team's names are not at the end of the alphabet, you should have received things by now, and the rest should come out sometime this afternoon. On project 2, let me suggest that you want to, those of you who feel you're under the gun, do some strategizing. I mean, there are certain, obviously you know the way that our tests work by now. There are certain things that we do, like, for example, print statements that had just better work. So sort of work your way up from that. All of the tests will probably contain print statements so that we can see whether they're executing properly. Then you can work on, say, scope rules more or less independently of typing, because there will be some tests that just do have nothing but plain ordinary local variables and no class definitions, and then there will be other things that have class definitions or that refer to attributes. And so, get things. Just remember that. Just try to work things up so that you've got something working. Because I noticed that there were a number of people who actually submitted programs for Project 1 that actually almost worked in the sense, and they would have these simple little errors in them that wouldn't, for example, they'd have test cases, some of their own test cases sometimes, that wouldn't py on parse because they'd made a slight mistake in the syntax of a slight, and I might add, very easily correctable error in the syntax of their ASTs, one that they could have fixed in minutes. And so that suggests that they had sort of gotten into a bind at the end, and had not pushed some examples through, because even very simple examples in these cases, they would have seen the problem. And so I think you should probably strategize to avoid that. Try pushing some things through your system and make sure that py on parse and so forth works. As somebody noted on the news group or noticed on the news group, we do py unparse. We use this minus minus alpha feature that refers to alpha conversion is the reason where that comes from. Basically what that does is it changes the name, it randomly changes the name, not randomly, but it changes the name of local variables according to what decals you've attached to them. So if it sees two local variables with the same name but with different decals, it gives them different names. So that when it's actually run through, when the unparsed thing is run through Python, it will, the scoping rules will be more or less the way that you made them, as opposed to the way you say they are, as opposed to the way that they look in the program. So it's basically a check that you've actually done what Python requires you to do. So that's you can use that. It's right there for you to use, and feel free to use it. Right? Remember that you are also be sure that you get at some point you'll want to be doing the various checks that are called for, mostly type checks. So when you get to that point, make sure that you do the checking as well as the type determination. So as I say, just try to do things. You can do things a piece at a time, and just try to push through something that works early on. Did I see a hand? Okay, let's talk about exceptions. So we segue from continuations into exceptions, which is why I wanted to at least start this today. So one of the things that you can do with continuations is you can say at some point in your program, save this point in my program, and if later something goes wrong, save it in a place where I can get at it from elsewhere. And if something goes wrong elsewhere, that can just call this continuation and jump back to where to the sort of state of execution at the time I had just called the problematic function and take some error return. That's fine, except it's a lot of machinery to do something that can be done much more easily, because exceptions always work in a particular way, which is that you are nested deeply inside, you are nested inside some function that you've called, and you return through all of the functions up to some caller who is still active. In fact, that caller is still, in effect, waiting on the call that causes the exception. So that fact means that you can implement these things a lot more easily than the general continuation thing that we showed at the end of the last set of slides. So, you can even, in some languages, you can not only return the exception, but in Java and C++, you can return a value along with the exception. But that doesn't really change things at all. I mean, once you can get the main effect, the special effect here is somehow getting from some arbitrary point in this function that you're executing way back to some caller that you don't know about at this point where you cause the exception. You don't know about the caller. You don't know who's called you. But somehow you get back there. You don't know how many levels of return you're going to have to do. But somehow you get back there. That part, that is the magic. And getting a value, transmitting a value back there, well, that's the easy part. You can think of thousands of different ways of doing that. So we're not really going to go into that part very much. All right, so what do we do? As far as language design is concerned, well, the language design, the first thing you can do is nothing. This is the C approach, the original C approach. We don't have exceptions. Instead, what you do is you have some convention for returning an error indication as the function return. So in the C library, you see a lot of this. You see it returns 0 if it's okay, and it returns something else if it's not, or it returns a value, a pointer if it's okay, and otherwise it returns null if it's not. And we set this value, this little integer value, erno, to indicate what the problem was. Okay, well, all right, well, that has the advantage of being simple. It requires no additional language features. And what's wrong with it? I can think of several things. Can you? So again, solution is no special language features, just return values that indicate whether you have an error. Yes, in the back. Right, that's the major thing. In fact, that's what almost everyone does. They forget to check the return on malloc, and on everything else, I might add. And they just go on and use the value. Fortunately, that usually causes a seg fault, but sometimes it might not. Right. So there's that problem one, making sure your nose doesn't get rubbed in the problem, and you can easily miss situations where something goes wrong. So what do? Well, you introduce new functions that are just like malloc, except they blow up when they return a null value or something like that. So you do a little more. The programmer does more work. Any other problems with this? Yeah. Well, there's a different mechanism for doing that. That's true. That's right. I mean, you have to have something for that. And as it happens, in fact, oh, good. Well, actually, that gets at another problem. Something about it. Functions return a value, but now you want them to return a value and an error value. Okay. Well, now all of a sudden things are getting a little troublesome. So, yes.
Well, you're basically leading up to it, but what if the expected exception is of a different type of return? You're expecting a string typical error code.
Right. So I don't have that flexibility. I have to return whatever the function type returns, and I don't have functions that we can return multiple values. So I could have a new feature that is functions returning multiple values, but that is a new feature. So in other words, it would seem that in order to avoid adding a new feature, I have to add a new feature, and so that's not so good. So let's see, do I have it? Yes, forgetting to check code clutter. Oh yes, that's another thing. So you have this all of your code has these explicit checks in them at each point. Allocate something, malloc foo equals foo char star foo equals malloc blah blah blah. If foo equals null, then blah. And so the things get a little bit hard to read. And there is also the fact that you have this slight cost in always checking these error codes, although that's probably the least of our problems. So along came exceptions to solve this problem, and we will look at them in more detail on Monday.